Hello, my name is Feynman. Today I'll be talking about a heavy-tailed algebra for probabilistic programming. This is joint work with my colleagues over at Berkeley and ICSI, Liam Hodgkinson, now at the University of Melbourne, and Michael Mahoney. The goal of this talk is going to be about approximating probability densities. And what I mean by that is, given some target probability density P, we're interested in choosing a good approximation Q. And the things that we would like Q to satisfy are as follows. In kernel density estimation, we want P to be Q close to Q, where Q is structured as a linear combination of existing points that you've already sampled, xi, weighted by some kernel function k. Or in variational inference, Q is chosen from a family script Q here, such that the chosen representative Q minimizes elbow. Here I've written with calf. There are two requirements that we would desire about Q. The first is that the tails of Q should be close to the tails of P. Intuitively, what you should think here is if P is heavy-tailed, then you certainly want Q to be heavy-tailed as well. And this excludes a number of models, such as non-conjugate models, where you may use a Gaussian approximation to approximate something whose target you don't know. The second requirement to ensure that this method either improves upon or matches existing work. Throughout this quick presentation, I'll be using this illustrative example to demonstrate how everything's working. Here I just have two prior random variables, n and x, both half normal, and I've defined this functional x2 as just the ratio of x and n. If you are very good at probability, you may recognize that x2 has a Cauchy tail. If not, we can use the generalized gamma algebra, as we'll see, to not only show this, but use this to construct good variational approximations a priori to sampling. Our analysis will depend on the generalized gamma family, which is any non-negative random variable that can be written as, in this form, x to some power nu, e to the minus sigma x to some power rho. So this will include things like, in particular, student t's, wherein the degrees of freedom will be equal to this new parameter. It also interpolates between other distributions, like the sub-Gaussians. In the paper, we provide details showing how operations such as addition, multiplication, exponentiation translate to operations on the generalized gamma random variable parameters. Continuing our illustrative example, we can now use the developed generalized gamma algebra to analyze the abstract syntax tree and determine that, in fact, our target is generalized gamma with nu equal to 2. In order to satisfy requirement number 1, we know that we need to choose an approximation Q that falls within this generalized gamma family. One way to do this is by Lipschitz normalizing flow transforms of parameterized base distributions. The idea is this. If we can match the base distribution's tails to that of the known target, we can apply a Lipschitz transformation of the bulk, which does not affect the tails, but achieves good and expressive modeling of the bulk. And it's illustrated here. We have a target distribution shown in green, and we're able to identify that this blue distribution is a candidate whose tail matches, as shown in this right figure here, where the two slopes are the same. However, at first the bulk is not well approximating, so we need to precompose a Lipschitz normalizing flow that transports the bulk, or the distribution's mass, such that after transformation, the candidate composed with the flow achieves this orange line, which is much closer. The tails are unaffected in this transformation, as evidenced by the two diagonal lines with the same slope. That's it. We now know how to analyze the target distribution's tails, and we know how to initialize an approximation that matches its tails and is also able to capture bulk expressiveness. When we apply this to a toy example, such as a sum of student t squares, we'll notice that the generalized gamma algebra's approximation is able to accurately capture all of the tail in this QQ plot, whereas a Gaussian-based approximation's tail is too light and levels off far too early. In this example, we show that the one-dimensional marginals obtained are much closer across a number of Bayesian linear regression examples. On the left here, we can see that every example which uses GGA approximations attains samples which are very good to the theoretical quantities. In conclusion, we've seen how the generalized gamma family can be used to model tail asymptotics in probabilistic programs. We've shown how to operationalize this model in order to generate optimized density approximations during the static analysis of a probabilistic programming language compiler. And lastly, we've shown in a number of examples and additional benchmarks in the paper how this results in improvements of tail approximation without compromising goodness of fit measures such as log likelihood and elbow.